And if you remember this, okay, so we made the Wiener filter, which is this estimator, which is estimating the output given x. Okay, so you know I know the x. And what we derive that in case of stationary processes, the property of the filter A depends on the power spectral density of this guy here, the correlation between this and that, and the power spectral density of Z. That's the dependency. Okay? So the way to derive is by orthogonality condition. And the orthogonality condition says that the error and the input in Z transform should be orthogonal. That's all. Now, what, you know, in my experience, this is one of the subjects that you learn quickly. Almost never seen one mistake, one error in applying the Wiener filter. I don't know why. Probably that's because it's easy. Okay, so you know. But anyway, let me. In any case, you know what we apply the orthogonality. We run it. Okay, we manipulate our basic assumption on the problem that we're solving, and then we came out. So I jumped to the end, and then we came out with this estimator. Now, this is the optimal filter. So Wiener is the optimum NMSC filter, which is minimizing mean square error, regardless of of any possible no station gradient. Now, what this or that? What you did not have captured last time, the reason why I'm considering, is that the Wiener filter is causal and anti-causal. So it's arbitrarily led. Now, in order to focus on about this point, okay, even if my intention was not to make example, but I mean, before making another step forward, I want that this concept is very, very clear to you. So I take this and I make an example on this one, this is specific, okay? Now, so once again, it was not my goal today, but you know, I mean, on coming, I said it's better that I focus about this right now because I mean, you're fresh. So let's take this and let's assume that Hz is equal to 1 minus rho z to the minus 1. Okay, so that means it's one pole. Okay, now, so let's substitute this into our equation of the Wiener filter. So what comes out is this is the following. That according to the assumption, I have a sigma square. Now, by the way, let me do a trick. I divide everything by sigma square w, and then you know I have a ratio sigma z divided by sigma square w. So you know, simplify. Then my filter is 1 divided 1 minus rho star z divided by sigma square z divided by sigma square w plus, now this new filter is 1 minus rho z to the minus 1 minus rho star z. Okay, so that means that, let me call this guy rho, okay, so just to simplify the life. So, you know, when I group everything all together, okay, it comes out as a Wiener filter, that my Wiener filter is all the way here. So it is 1 minus rho z to the minus 1, and then it's divided by rho 1 minus z rho z minus 1 minus rho star z plus 1. Okay, so now this is the optimal filter. Now this optimal filter contains 1 0 and 2 poles. Now these 2 poles are one inside and one outside of the circle. So because of the structure of the 2 poles, now see, first of all, since I have 2 poles, the impulse response is infinite. Okay? Since I have 2 poles. So what I can comment here is that, you know, the filter, so according to that, I can conclude, I write here, I can conclude that the impulse response is infinite. Is between minus infinite and plus infinite. Let me write this, okay? Second remark is that, you know, the impulse response, so rather than writing impulse response, use the AN, okay? Then AN is positive and negative. So it's causal and anticausal. So the Wiener filter is causal and anticausal. And, you know, and the impulse response extends from minus infinity to plus infinity in general. Now, you might find a specific case where the filter is not, has not this property, but, you know, in general it's this way. So you need to imagine that, you know, the Wiener filter, it might be something like this, okay, which is going from one side to the other side. So, I mean, it's long, okay? So usually, you know, it's not trivial to apply a filter that long, okay? So in engineering way, I mean, the filter, any filter is a multiplication. Any multiplication is a usage of a computer. So try your whatever algorithm and make your algorithm with the filter very long. Then you know that you need to wait for a long time. Make a filter very short, you know, you get a response very quickly. Even by macro. So every multiplication in hardware is carried out by specific circuits. And, you know, and it takes time. Okay? So when I make a filter very long, I mean the hardware is taking a long time to make it. And, you know, a filter is a set of multiplication and sum. Because, I mean, it's a multiplication for the coefficient and then summing all. So that means that I can say that the filter has been already, the output has been already computed only when the filter, every coefficient of the filter has been multiplied by the corresponding input and sum all. That means that all the multiplication should be finished, not just a few. So this is what is telling to an engineer about that. So since all the multiplication should be completed before declaring that the filter has completely estimated in this case, but, you know, completely made its job, or the filter job, then, you know, for this reason, the Wiener filter is a beautiful, perfect, how can I say, perfect, you know, very beautiful, analytically beautiful filter, but practically, you know, it stays there, okay? Because, I mean, about the support of the filter, about the length of the filter, okay? Now, what you can do is that, as I told you the last time, you can take these impulse response and truncate, and then you can say that everything here is zero and everything there is zero. Now, this filter is not the optimal one, because you are cutting out something, okay? So, if you take a Wiener filter and you cut it, it's not an optimum Wiener filter, okay? So, if you have to cut the filter, then my recommendation is write as a matrix, okay? Now you start all the puzzles start to take the place. So why we started by block processing? Because in block processing you have a piece of data which is compliant with the data that you gather. Perhaps, you know, you have a piece of song, you have a piece of vibration, you have a piece of whatever in communication. You have a block which is called packets, and then, you know, you process that. You process it as it is itself. Then you have a new one, you process overall, and so on. So now this was a comment that I wanted to freeze clearly in your head. The reason why Wiener filter is really beautiful. I mean, the theory is very elegant, you know, and so on. But as always, it's like the ideal low-pass filter. The theory is elegant, but I never seen applied in practice. Okay, because the impulse response is causal, anticausal, and you know, and the tail goes between minus infinite to plus infinite, and then you need to truncate in some way and so on. Okay. Now, this was just a remark I want to do. Now, we did a linear prediction. Okay, so the new topic I want to do today, I want to do two topics today: the linear prediction and start the Bayesian tracking, as I wrote. Okay, so we made the linear prediction until the break, and then we start the Bayesian tracking. Now, about the linear prediction, actually, the problem about the linear prediction is something that we already treated in some way. Actually, we started about linear prediction. I didn't call the linear prediction at that time, but you know, probably I did. I don't remember. Okay, so you know, I mean, it's one of the fundamental tools that you need to have in your box, in your toolbox. Okay, remember, you know, my goal is to give you to complete all the pieces in your toolbox, so that you have all the pieces there, and then you know you use when it's the time. Okay, I need to tell every piece what is the limit, what is the performance, what is the accuracy, and what is this, what is that. Then you know it's I mean the implementation depends on your specific problem, the problem you are paid for. Now, so let's look at the linear prediction. I mean, my goal is to show that linear prediction has a very strong relationship with the autoregressive random process. Now, one step back. When I have an autoregressive random process, you remember, because you did in the intermediate test, okay, you remember that the autoregressive random process, the autocorrelation, is equation dependent with the coefficient of the all-pole filter by Euler-Walker. Okay, so Euler-Walker is right here. So what we saw in the autoregressive is the following: if I have a Y process which is filtered by a filter that is 1 divided by A Z, and this A has n coefficient, okay, which means writing this way means that this polynomial is monic, so I have 1 plus A 1 Z to the minus 1 plus A to Z to the minus 2 plus A and Z to the minus n, okay? So what we saw that the output of that, we call that Xn, is autoregressive random process of order n. This is what we know. In addition, we know that there is a link between the set of coefficient A and the autocorrelation Rxk. Okay? And the link between these two parameters is Euler-Walker. This is what we found. Okay? In other words, if I know this, I can get that. If I know this, I can get that. This was, let me say, this was the scope of the intermediate exam. The scope of the intermediate exam was to let you get practice on this, usage of that. So every time you see every time you see a whole pole filter, you immediately can calculate, at least virtually, can calculate immediately the set of the autocorrelation coefficient. Okay, you can calculate, using the ensemble. So that means the true autocorrelation, not estimated. Because if I give you that, I tell you that this one is a random process with the power of sigma w squared. You can calculate the autocorrelation exactly, not approximate. It is exactly. Okay. So the link between this and that is the Euler-Walker. Now, freeze that, and let's go to this new, apparently innocent, new, and totally uncorrelated part with what I'm writing there. Now, let's see the conceptual, okay, and some notation, okay. Now, a linear prediction. What is a linear prediction? Linear prediction means that I take a set of coefficients here. Okay, so I take all this in a shaded area, which goes from xn minus p to xn minus 1 to estimate xn. Okay, so my goal is to estimate the x at the end position using all the data, okay, that are previous to that xn. So, you know, if my time is n minus 1, then, you know, I'm predicting, I'm estimating the sample at the position n. So, then, you know, I indicate as the estimate forward, okay, forward, you know, is the estimated value is x hat pn. Now, is hat because I'm estimating, is p because it's reflecting the order, so how long is the estimator, okay? And now, you know, the difference between this x hat p and xn is epsilon, which is the error. So this epsilon is the prediction error, okay? So let's sketch it. Now let me add a new word, forward. Now the reason why I put forward is because, I mean, since I'm assuming, which I forgot to say, but since I'm assuming that, you know, xn is a stationary, then, I mean, in any stationary random process, the time can be reversed. So I can similarly do the same, which means I can take my filter coefficient, flip the filter coefficient, apply the filter coefficient on the same data after flipping, and predict on the past the sample x n minus p minus 1. Now, this prediction is carried out on the backward side because I'm predicting on the past. Okay? Now, since the process is stationary, statistically, the property of the forward prediction and the property of the backward prediction are the same, statistically. Okay? Which means, if I take the error, now this error is beta p n minus 1, which is, you know, the backward prediction error, beta, of the prediction length p, which is computed on the sample n minus p. Should be n minus p. Okay, so it's here. Now, you know, it's here. Now, I mean, the statistical property of this guy is the same as epsilon p, which is a forward. But what is the beauty? Is that I know epsilon, because I'm predicting in the past. And I know all these samples. So what I can do is use this error to improve the prediction forward. Because I don't know the future, I know the past. So I can apply the same filter to predict the past. Okay, so this beta is backward. Is backward prediction error. Okay, now look at specifically these two using the same data. Okay, so forward prediction and backward prediction are using the same data. Now, we remember that, okay, and by the way, you know, the forward prediction is the hat down and the backward prediction is the hat up. Okay. Now, let's enter a little bit into the notation. Now, what is the forward prediction? So x at p here. Now we saw it is a linear combination of all the samples starting from n minus 1 to n minus p. So, you know, it's a linear combination because it's a linear prediction. So I write it this way. So it's a linear combination of x n minus k, where k is going from 1 to p. So, you know, I'm taking all this data, multiply by that, summing. Now, this minus is only for technical reasons, because there is another term that simplifies. Okay? So this minus is only for technical, for the proof. So writing all that in matrix form is filter, okay, which is a row vector, time a column vector, and this xn is this block of data. Okay. Now, so what is my goal? My goal is that I get to my prediction error. So my prediction error is epsilon p, and then is the prediction error is equal to xn minus x hat n. But since x hat is defined for minus, then I get that my prediction error is xn plus something. Okay. Now, I need to estimate a set of coefficients. So to estimate a set of coefficients, I use the orthogonality. So by using the orthogonality condition, the orthogonality says that, the filter coefficients are obtained by putting the orthogonality between error and sample. Okay? So this orthogonality condition is the same as orthogonality between epsilon pn and the vector xn, complex conjugate, okay, which is equal to, in case it's complex. Okay. So this is the orthogonality condition. So that means that the epsilon is orthogonal to the first sample, epsilon is orthogonal to the second, epsilon is orthogonal to the third, blah blah blah, and then up to the p sample. Now, if what I do is I now put the information. So what is epsilon specifically? And so the epsilon is xn plus sum of a, or rather than the sum, it is a0 AP transpose xn. Now the first is a scalar, the second is a vector. Now, manipulating again, okay, I get that it comes out that, the set of equations are the Euler-Walker equation. Okay, so, the Euler-Walker to go one side, and I get the Euler-Walker for linear predictions. Okay, so, at least analytically, it comes out of the same set of equations. So, we already discussed that, so, I write a matrix, the matrix is structured this way, is third place, I get the linear prediction. So, if I need a linear predictor, then I put all the coefficient, which is on the matrix, it is third place structure, so I have R0, R1, so I have R1, R2, R3, so it's, the structure of the matrix is a diagonal, okay? Now, this matrix multiplied by the set of coefficients, which is the filter, is equal to this vector, and this vector contains, look at here, contains, the set of autocorrelation coefficient at the position at the leg 1, 2, 3, and 3. Okay, so that, I get my, let me say, my linear predictor. Okay, I invert the matrix and it's over. Fine. So analytically, it's closed in this way. Now, let's see one comment before I continue, because I don't have the slide in the slide here. Now, in case I have more than one comment. Okay. So in case I don't want to make a linear prediction of one step, but I want to predict 20 steps ahead. Okay. Suppose that I want to predict not from now to 1 second more, but if I want to predict from now to 3 hours more, it can virtually be done. So what I need to do is to rewrite all the problems so predicting L step means that, you know, I have my signal, and my signal is composed by P samples, and these P samples are Xn, okay? And then I can use it to predict L steps ahead, okay? Where L can be arbitrary. Of course, a linear predictor that we saw is one step prediction, okay? So I estimate one step ahead. But I mean, imagine that I want to use the predictor to estimate 10 days. You know, I can virtually do it, okay? So if I need to predict very far away, then what I expect is the following. Now, if I have my own data, and I want to predict forward one step ahead. So I expect that the predicted value has a certain error. And you know, so the error is the one that we can analytically calculate. But you know, before analytically, listen to me. So I have a certain error. So this error is the error due to the predictor of a length p of L equal 1, so one step ahead at the sample n, okay? Now, but this error has a certain sigma squared error, which is due to the predictor of a length p and on the prediction forward L, okay, where L is equal 1. So that means that my prediction error, you know, if I look at the mean square error, my prediction error has a certain dispersion. Okay, this is what I expect. Now we can calculate analytically, we will do in 1 second. What's happening if I try to predict my very far away? Now, you know, if I try to predict very far away, I mean, what I expect intuitively, I'm not touching any equation, what I expect intuitively is that if I'm estimating, so if I'm making a prediction of one step ahead, I get a certain error. Estimating much far away, I get a larger error. Because I mean, I'm using this set of data, which I indicated here, to predict what's going to be there, okay? Where there can be, so 10 days ahead. I'm using the stocks of value that are shaping, okay, this afternoon, but in Italy there is a stocks, okay, even this morning. So, you know, I can look at what is the stocks behavior or whatever company, rather than predicting the value in 10 seconds, I try to estimate the value in 10 days. Okay. Now, what I am going to expect? I expect that estimating in 10 days, my dispersion is growing. Okay. Intuitive, right? Not touching anything. So what I expect that my dispersion is growing, okay? Which means that what I expect is that the sigma square epsilon, which is the power of the prediction error, for a linear predictor P, okay, and for L larger than 1, okay, is growing, okay? So intuitively, you know, I can always use that, but I expect that this one is growing with L. The far away I predict, the worse I go. Okay? That's the one. Do you have a sun? Do you have a sun? She's shining. Is okay? Okay. So, you know, it's growing versus the length. Okay? Now, Remember that, because I mean it's a property that we will take advantage in a while. Okay, so one was this comment. I have two comments in my hand. See? Okay, the formula for the P predictor is this one. Copy so that you are on the same page. Here. Okay, then you have the formula for the predictor. Let's see again. I was telling you, the story of forward prediction and backward prediction. Okay. Now, in our course here, we will not use the property of the backward prediction. So the second comment is the following: if you want to calculate a linear predictor in a real case, you cannot do it as we were discussing about the adaptive processing. So in adaptive processing, I mean, what we avoided that we wait for a long time of data, we collect the data, we build the correlation matrix, we build the autocorrelation, the cross correlation. We try to create this sample estimate of the matrices, and then we calculate the filter. Okay, this is what we avoid. Now, if you want to do the same for linear prediction in a non-stationary environment, you can do exactly the same algorithm, which is you can make an adaptive linear prediction. Now, the way to make an adaptive linear prediction is by taking into account that if I make a prediction forward, I get x hat. But in practice, I don't know x, because if I knew x, then the problem is finished. So this error that I could calculate, if knowing the statistical property of the signals, it can be done, it can be calculated in practice by implementing practically the backward prediction. So what I'm saying is, in adaptive filtering, what we did is we were comparing theta minus theta hat. You remember? And then you update the filtering by comparing this error with this is the error with the data that you collected, and you build the adaptive filtering this way. Now, if you want to create an adaptive linear predictor, what you can do is you need to take the past. So the error that you can calculate to update the adaptive linear prediction, adaptive, which means varying, linear prediction, is that you can use the past to update the filter that is used for the future. So the second comment is, if you want to use the linear prediction in adaptive form, you need to take into account that due to the stationarity of the random process, you might argue, but you say it's not adaptive, so the processes are not stationary. If you want to use the linear prediction for a non-stationary environment, provided that the degree of non-stationarity preserves the property of stationarity within the time frame of the filtering, okay? So I said it's non-stationary, but within this time window, which is the time frame of the length of the predictor, is stationary, then in this case, you can use the error on the past to improve the accuracy of the estimator for the future. Is it clear? Should I say? You have a movie, right? It's a popular movie. Give me the link. Give me the link, because someone gave me the link, I found it. Then I saw, my kids wants to put the flag on, I like it, with my account. So Did they put? Ah, he did?
Yes.
Okay. Because he said, I put it. I said, no, please. Okay. So, did he manage?
Yes, because I uploaded it. I did it. I received.
Okay, I'm going to tell him this evening. I said, because I mean, he put it, and then I said, what did you do? Did you like it? Do you like it? So, he was listening. Okay, so I said, do you like it? Yes. I put a like. I said, why do you do it? With my account. Come on. No, I said, okay, then I am flagged. But Okay, so, yeah. So you have a record, right, about the story. So, this is useful in case of you have a non-stationary, you need to make a linear prediction for a non-stationary process. Let me tell you one application for linear prediction, okay, which might be useful before entering into the discussion about the autoregressive. Now, the linear prediction is very used. So it's one of the signal processing tools that you must know. Now, you can make a linear prediction. For instance, if you want to understand if in the signal you have a process that is changing in a property. Now, let me make an example. Imagine the example of the spikes. Okay? So you have a signal, and then after every now and then you have a spike. Okay? This is the signal. Now, imagine that now in the signal you implement a linear prediction. Okay? So what comes out from the linear prediction? Now, the linear prediction, is trying to, is taking this to predict the sample there. Now, the prediction is not perfect, because otherwise, if the prediction would be perfect, then you have a perfect predictability. Okay? Now, if the signal is perfectly predictable, which might exist, okay, a signal perfectly predictable, then that means that the signal is deterministic. So a perfectly predictable signal are, for instance, a sinusoid. If you take a sinusoid, the sinusoid is perfectly predictable. You can try. Using the linear prediction, you can perfectly predict the sinusoid. That's a property, very strong property, which is used for high resolution method for frequency estimation, which we will not cover. Perhaps if I have time, I want to give you some insight. I'm not touching it intensively. Now, let me go to these examples. So I'm taking this set of data to predict that. Okay? Now, what I get is that my prediction, so if now I represent here on this axis, this is the axis n, this is the axis n. Here I have xn, and here I have epsilon. So the prediction error, okay, versus time. So what I get is my prediction here is, is here. The error, this is the error. So this is epsilon. And then I take this error and I put a point here. Okay? So what I have in this new axis, I have a prediction error. Okay? So then I have this prediction error which is going up and down. Then I'm here on the spike. What's happened on the spike? And the spike, it happens that if using all this data to predict this sample, I have my prediction value, which perhaps goes here. But the spike is there. So my prediction error on this sample and hat is big. Okay? So what I get is that my prediction error, is going up. And then it's small, then going up. Small. And what do I see? I see that in this case, the spike is destroying or is an outlier on a setting which is easier than there. Because I have a Gaussian, and this guy is Gaussian with a certain, a standard deviation, a certain variance, and then I have a big one in the middle of nothing. Okay? So if the process is correlated, finding the spike by using linear prediction is optimum, is an optimal way. Okay? So you can use a linear prediction. Anyway, you put in the box. So what you can do is that, you estimate the value of the spike. Okay? You evaluate that you have a spike. Then, in place of the value of the spike, you put in place of that, in place of the spike. Once you recognize the spike from the error, you put in place of the spike its prediction, and then you move forward. So you are basically cutting, eliminating the spike, and replace the spike or the big value by their prediction. It's possible, you can do it. Now, if you ask me, which is the optimal way, I'm not telling you, because I don't take the responsibility to tell you which is the optimal way. I tell you that it's one of the possible implementation of the linear prediction. If you are in trouble, you have a set of spikes, try to implement a linear prediction. Try to implement a trick, because when I say that I isolate the spike, I have a linear prediction, I get a big error, I replace the value here with a predicted one, which means I need to take a decision. Are you error bigger than a certain value? Replace the value with the predicted one, or continue. So that means if epsilon p and n, okay, square is larger than a certain value, okay? If larger, then, okay, if it is larger, then replace x n equal x hat and else, if it is, smaller than that, leave as it is. So it means x and naught is equal to x and naught. Of course, I'm not writing a code. And it's a pseudo code. So what I'm saying, when you do this kind of trick, when you replace the samples of one signal with the signal of another coming from another origin, okay? When you do this kind of trick, remember it's a non-linear. It's not a filtering. It's a condition filtering. Okay? So it's like you have two signals, the predicted and the true one. And then you decide which one is better. Okay? That's one possibility, as I said. There are many others, but Now let's go to the exercising part, which is, let's go to the parallelism between, the linear prediction and autoregressive process. Okay? So, 3 slides. Yeah, right. Okay, so, this is where, what I'm doing here is a conceptual part and exercising part. Okay? Now, conceptual part, what I say is, now, if I need to get the autocorrelation, okay, from a set of coefficients in a setting like this, okay, then everything is ruled by the Euler-Walker. But now in the previous stage, I found that, if I know Rx, x, k, what we found is that if I know Rx as k, then I can get a set of coefficient A, that is, this guy is a linear prediction. Okay? So this is what, what we found. So, but there is a strong correlation. Now, the strong correlation is the following. What about if I apply here a filter A, Z, that has a set of is a linear prediction that has a set of zeros that are exactly the zeros that cancel with the poles. That means if I make a linear prediction here that has a length n equal, let's put n0, equal to n0. Now, since I take the autocorrelation comes from this, and this comes from the Euler-Walter equation, then since the sample coefficients are coming from the same Euler-Walter equation, then what my linear prediction is perfectly estimating the set of roots that are exactly the same as the poles. So that means that the linear prediction this way is performing a perfect whitening for an autoregressive random process. So in this, for the length exactly coincident with the length of the autoregressive random process here. Okay? And the output, what is the output? The output will be Wn in this special set. Now, so let's look overall. Okay? So in general then, you know, I can virtually always look at the cascade of an autoregressive, so up to here is autoregressive, order n0, with a cascade of a linear prediction order p. Now, I change the notation. P. I realize that. Okay. Now, so if my linear prediction, my linear predictor has the same length as the autoregressive, since the equations are the same, then my linear predictor is perfectly whitening the process except. Perfectly whitening means that the process auto is white. Epsilon P n is perfectly white. It cancels perfectly the poles of the autoregressive process. If P is if the order of the linear predictor is smaller, less than the order of the autoregressive process, my linear predictor is approximately whitening the random process outside. It tries to do the best to whiten the random process outside as much as possible. Okay? So, you know, what comes out that the linear predictor tried to put by zero canceling the poles as much as the autoregressive, as much as the linear prediction can do. Now, looking what happens, you know, by movie, let me say, consider a case where I have an autoregressive, which is obtained by Wn, and I have a filter composed by 3 poles. And Xn here is autoregressive order 3. And you know what I do here, I put a linear predictor, and here I get the prediction error. Now I can also compute out of that the power spectral density of the error for arbitrary p, okay, which is simple. Is the autocorrelation of the prediction error computed for z equal aj, okay, which is something that you saw. Now let's look at the movie here. Now let's consider the case where, you know, my linear predictor is doing nothing, which means my linear predictor has a prediction length which has a predictor length which is equal to 0, which means no prediction. Okay. Now, so if there is no prediction, then the power spectral density here is equal to the power spectral density here. Now, if the Xn is an autoregressive order P, and if so I have 3 poles, then assuming that in Z plane I have these 3 poles in this position, then that means that I have a 1 resonance, a 2nd resonance, and a 3rd resonance. So, you know, I have a, oh, this plot has been flipped. In the book is wrong as well. So, it's wrong, it's, let me write here. No, it's my cross here. Let me rewrite. That's a pity. So I have 3 poles, and the 3 poles are, oh no, 0 is here. Oh, it's correct. Sorry, I need a copy. Okay, so I have a pole here, another pole, another pole. Okay, so I have a pole at the frequency omega 1, omega 2, and omega 3. Okay, now since the pole omega 1 is for negative 1, so that's the frequency of omega 1 of the first pole. Okay. Then I have the 2nd and the 3rd. They are approximately at the same radial distance. So that means that they are giving me approximately 3 resonance, omega 2 and omega 3. Now, the power spectral density before touching everything is this one. So I have a big resonance, and then I have 2 maximum here, approximately. Okay. So this one is the power spectral density of the signal Xn, which is the autoregressive. Now, we have seen, we learned by looking at the adaptive filtering that if I use this random process to make an adaptive filtering, the speed of convergence depends on the ratio between this and that. So if this one is very peaky, and if this one is very small, then the convergence ratio might be slow. Okay. Now, anyway, so assume that my goal is to perhaps to pre-widen that. So try to cancel as much as possible the influence of the 3 poles. Now, let's see what's happened, what I'm going to do if I put a linear predictor order 1. The linear predictor order 1 is computed by the Euler-Walker equation because it's always that one, okay? Which is the same as in the intermediate exam, calculate the autoregressive order 1 random process given the autocorrelation of the process itself. And so you computed that time, okay? So this is by how technically it should be done. Now, what is the power spectral density in case I calculate a linear predictor order 1? Now, if I try to pre-widen this power spectral density by simply 1, 0, because this is what I'm doing. I'm trying to compensate these resonance by using 1, 0. So, since you have 1, 0 to spend, the algorithms try to put a 0 in order to cancel as much as possible the influence of the dominating pole. Okay. So, the 0 will be collocated, will be allocated in this point here. This point is the point where, I'm close to cancel the influence of this pole. So, if I put close here, this 0 is trying to cancel as much as possible the influence of that pole. Now, in power spectral density, which is the power spectral density which comes out here, is an autoregressive order 3 convolved, okay, so it's a filter by 1, 0. The 1, 0 is trying to cancel the influence of all 3 poles, but it has 1 degree of freedom versus 3 because I have 3 poles. Okay, so by cancelling the power spectral density after this cancellation is this one. Okay. I try to cancel as much as possible, but it's not flat. The power spectral density is not constant because I have 3 poles versus 1, 0. Now I try to put a linear predictor order 2. So what I do, I take a linear prediction order 2 here, and I try to compensate by making linear prediction all the 3 poles. But since I have 2 zeros, so the 2 zeros are not able to perfectly compensate the power spectral density. And then what comes out that my power spectral density after that is not exactly flat, because it has a residual fluctuation, because the pole and zero are not perfectly compensated. Now, on the other hand, if I put 3 poles, if I put 3 0 versus the 3 poles, I perfectly cancel. Okay? So, now, this means that this is giving us some ideas how to calculate the autoregressive power spectral density, or to calculate what is the order of an autoregressive random process, in case I don't know. So in case I don't know how many poles are in the autoregressive random process, so imagine that this part, you don't know this part here. So what I can do, you can make a linear prediction. So you start the linear prediction order 1. Now, is it the output white? No. Okay. I go with the linear prediction order 2. Is it white? No. I can start with the linear prediction order 3. Is it this guy white? Yes. Okay. That means that Xn is autoregressive order 3. So, the order of the random process is 3. So, it has been colored by 3 poles. What about if I put 4 zeros? So what about if I make a linear prediction order 4? Since the linear prediction order 3 was already white, so there is no more to white. There is no more to compensate. So what I expect is that the 4th pole, the 4th zero, is not doing anything. Okay? This is what I expect. Now, in practice, the 4th zero, it might fluctuate. And perhaps it might distort a little bit the property of the estimated, the property of the first 3 estimated zeros, which are perfectly compensated in these poles. So, in other words, if I overestimated, if I over-parameterize the length of the linear prediction and the linear predictor here, it might happen that the zeros are fluctuating too much due to the over-parameterization, which means using more parameters than necessary. Okay? Now, so in theory, what I expect is a very easy way to look at the property of the autoregressive random process is that rather than measuring the correlation property here, it's easy to measure the power of the error. So what I expect is that, the more I increase the linear predictor, the more there is to predict. Now, up to a certain point when there is no more to predict, then, my power here is not changing anymore. So, this is what I expect. So I expect that, if I represent the power of the prediction error versus the length of the linear predictor, then, the more I increase the linear predictor, the lower is the power of the prediction error. Remember, it's in this chain. And, and sometimes this part is not accessible, which means you cannot see. Okay, so autoregressive order is not known. Okay, so imagine you take the music And you know, I ask you, I give you a music file, which I'm tempted to do. And you know, and I ask you, what is imagine that you parameterize these music file as an autoregressive random process. Question, what is the order of this autoregressive random process? Now, solution, I take the music file, I make a linear prediction. I start with linear prediction order 1, 2, 3, 4, 5, 6, 7. And then up to a certain point when, you know, there is no more to predict. And then, you know, the output, the prediction error is getting pretty flat. When you are in this condition, then you found the length of the optimal linear prediction or the order of the autoregressive random process. Okay. Now, do not expect to see such a nice plot, of course. Do not expect that the points are so clear. And you know, do not expect that increasing up to a certain point, increasing the prediction, the linear predictor is getting flat as in this plot. When you are in numerical or you are in practical setting, what you expect is that these are fluctuating. But at a certain point, you know, they're slowly there. Okay, so there is a kind of different slope. So up to a certain point, you know, this behavior is quickly decreasing, and then there is a certain point forward, then, you know, it's slowly decreasing. So there is a change of decreasing speed. So it's decreasing fast. And then up to a certain point, it's decreasing slow and approximately linear. And this is decreasing fast and approximately exponential. Okay? So, you know, your practical setting is that you have the error which is decreasing fast, and then you know, after a certain point is decreasing very slow. Then this crossing point is approximately defining where is the order of your autoregressive process. That is a nice. That will be a nice. Practical exercise that you do in the file. This afternoon I'm manipulating the file for the homework number 2. And, so the only way to let you study that is that I let you play with that.
So I don't get this one thing, but if I have NA zeros, should it be already the best I can get from?
If you have NA equals 0?
No, if I have NA zeros and NA poles,
okay.
should it be the best I can get?
Oh yes, but you know, I mean, due to the fluctuation, the linear predictor is always tries to predict more, okay? And then I mean, it's not flat. So it's slowly decreasing due to numerical problem. Because the algorithm try to predict as much as possible. And so, you know, sometimes there is a part which is left in the prediction due to the other piece of signal, then you try to predict more. This is the reason why you don't get this nice flattening, you know, it's a decrease in the speed that is slowly decreasing by increasing number of the predictor length. The other reason for that is the more you increase the predictor length, so this matrix contains the size of the predictor length. Now the entry here are the autocorrelation computed in 0. and blah 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 blah, and here are the autocorrection computed in p minus 1. Okay. Now the confidence of the autocorrelation for the larger time lag is lower than the confidence for the center one. For this reason, we will see that there is an implicit windowing on the data, which is it's a triangular shaped window due to the accuracy by the sample estimate. This is the property that we will see. So for this reason, if I get this matrix, and this matrix is very big, and in place of the true autocorrelation, I put the estimated autocorrelation. So the confidence of the last these samples are lower and lower and lower and lower. So this poor property is compensated, always compensated, by trying to enrich the property of the linear estimator. And then the linear estimator, even if in principle some of the values should be 0, they are not 0. In other words, if I make a linear predictor, and the linear predictor should be composed by 3 values. So if it is 3 values, so it's A1, A2, and A3. That's a polynomial. But you try to estimate A4. So the A4 is not 0. Okay? So it's fluctuating. A5 is fluctuating as well. Now, this fluctuation on A4 and A5 is in some way by fluctuating, is in some way try to make a prediction better, because the job is to make a prediction better. So it's the linear predictor is trying to compensate for the inaccuracy of the autocorrelation for a bigger lag, for a bigger distance, for a bigger value, and is trying to minimize as it is the job of the linear prediction is trying to minimize the power of the error. And so trying to minimize the power of the error, even if in principle there is nothing else to minimize, I try to predict the noise essentially. And for this reason you never get a flat, but it's decreasing, very slowly decreasing. So that's why what I'm showing you it's happening. Okay. So you don't get this nice flat plot, but it's slowly decreasing. Okay. And if you take a very big, like imagine here, you have 1, 2, 3, 4, 5, 6, 7, 5. This guy is 10, and I try to implement a linear predictor order 20. Okay. Now from 10 to 20, the coefficient should be 0, because my linear predictor, okay, is related to autoregressive order 10 random process. But because I'm using a sample value, the coefficients are still fluctuating. And this fluctuation is making the linear prediction trying to always minimize the error. So perhaps, this hedge does not happen exactly on the sigma squared W, so it happens on the higher point. And then it will slowly try to minimize that. That's what you experiment with. So you stop yourself, okay? You stop yourself where you get this hedge, okay? Where you have this discontinuity in the slope. Yeah, actually I should write here this way. So this slope is higher. Start and say, get this, is higher than it should be due to the presence of the inaccuracy of the coefficient that you estimate, because it's a sample value. So you don't have a true autocorrelation. You have the autocorrelation that you compute on data, and is affected by the fluctuation due to the limited length of the data. If the data is infinite, that's okay. But since the data are limited, in length, and you cannot calculate perfectly the autocorrelation. Furthermore, the limited length is also the length where your random process is stationary. So if you take a song, you know, you need to cut the song into pieces where the singer is singing and the singer is not singing. Because if you calculate the autocorrelation over all the music or the file, and the singer is singing here, not singing, 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 not singing, and you average all, so you are averaging the portion where the singer is singing and the portion where the singer is not singing. And so the autocorrelation is the average by putting that together with the place where the singer is not singing. Okay? Let's have a coffee. It lasts a little bit more.